Everybody, shall we get started? The last lecture before exam 2, which is on Monday. Let's do a few announcements. So exam 2 review session, Saturday at 4 p.m. Run by the TAs, just like last time. Come with questions. Most likely the best use of that time is to go over the practice problems, which I will distribute hopefully tonight, but probably maybe at some point tomorrow. I'm going to have an additional office hours on Sunday from 4 to 5:30 for those of you that want to hang out with me. And the exam is an untimed nighttime exam like last time. We have to start at 6:15 because there's a speaker in here until 6. So those of you that have conflicts, obviously you can start early to avoid the conflicts. Any questions about the exam? No, that was a 1.5 hour in-class exam that you had as much time as you wanted to take.
For the research, like almost everyone do at least 3 hours.
Yeah. Well, maybe it will be useful for me to give some incredibly useful exam 2 hints. Now, so anyways, those hints I hopeful were really useful, and those are the things I think you should study for the exam. Anyways, okay. So any other questions actually about the exam before we get started today? Oh yeah, those are pretty good hints, right? Yeah. Okay. So let's get started with the last major lecture of the course here. Okay. So last time we talked a little bit about not learning, but evaluating deep networks that had already been trained to perform some interesting tasks, right? And so we didn't really talk too much about how we got the network weights, right? So I wanted to have this running example here to kind of set the tone for today. We're going to talk about how we learn the parameters, these magical parameters of the network. And these are the computations that are running for days or for weeks to try and learn some of these parameters. And so there's a lot of interest these days in making them go faster, to parallelize them. Okay, so imagine that, last time I said, okay, here's a rough topology of a network that took as input an image, and the popular object classification networks might output a bunch of numbers which says, here's the probability that there's a particular object of this class in this photograph. But in this running example, I wanted to have a much simpler example, and if you notice, the output of the network is 4 numbers. And those 4 numbers I want you to think of as the input will take as input an image of a professor, and it will output whether or not the probability that this professor is, the only 4 types of professors there are, right? Easy, mean, boring, or nerdy professors, right? So if you hand this network an image, like an image of myself, the network will perform some inference, and it will say, I think this is the likelihood of what this type of professor is. So it's assigned the professor to a class, right? So this particular network has 4 classes. And remember, inside of here are like 50 to 100 million numbers. Many of them the weights of these convolutions, others just being weights of these matrices for these fully connected regions. And the question is, where did those 100 million numbers come from? Right? How the heck did we get those magical 400 million numbers where you give this network any image, and with some degree of reliability, it actually kicks out the right categorization? So in its simplest form, you can think about this as a learning by example exercise. So imagine you had a huge database of professor photographs, and that students on the web had taken some time to actually ascribe a label to each of these images, right? So imagine you had hundreds of photographs of all the professors here at CMU, and for some reason the students have decided to go online and crowdsource tag all of them with their opinion of that professor. So you might have all this data here, right? So in this case, like I decided to tag all of the professors, all the pictures of me as like nerdy professors. So that would mean that if there was an image of me that came in that was not in the training set, that was not sort of in the examples that I gave the network, that a good network would kick out an answer that says, oh, I'm absolutely certain this is a nerdy professor, because every time I've seen an image of this particular individual, I was told that the right answer is that this is a nerdy professor, right? Okay. Now, of course, the network might kick out some other set of probabilities here, in which the network is certainly on the right track. You could say that in this case, it probably got the right answer, because you might say, hey, I'm going to classify this as the category that's the most likely, right? In this case, nerdy is the most likely. But we would love for this distribution to match the target distribution, because this is the right answer. Okay. So the difference between the answer that we want and what the model is spitting out, what the network is spitting out, is the error in the network, or the loss. And so we can compute, we can quantify that loss in a number of ways. Like we could actually just take like the L2 distance between these two vectors, for example. A common loss function is the softmax loss, which is basically saying if this is the correct category. So up here, just for those of you that are going to raise their hand and say this is totally wrong, typically in these networks, the output is actually the unnormalized log of the probability. So you have to raise it to the power to get back and normalize it to get a probability. So this is basically saying that the log of the normalized probability of the correct answer is the loss. So obviously, if the normalized probability, if it was 1, then there would be no loss, because that would be the correct answer. Right? So that's some intuition behind a softmax loss. So you can imagine that depending on your task at hand, you might ascribe some way of measuring the loss given an input on the network. So we know how wrong we are. And if I give, for all of those training samples back on the slide, you could say that, well, I feed them through the network with the current set of parameters. I get out an answer. And that answer, if it doesn't match the probability, just the label, then there will be some loss. And the total loss of the network can just be seen as the sum of all of the losses for all of the training examples. Okay, so when I'm training, I'm just giving the network an example. I'm telling it what the right answer is. And so it can assess itself, well, how wrong am I? And we can compute the loss, right? So the intuition of training is that if I give you a sufficiently broad set of photos of professors, and it gets the answer right on all of those photos, then hopefully the values of the parameters are such that it will get the answer right on new photos, on any photo of a professor that I give you. So that's sort of the goal of training. And so to give you a sense of, well, how the heck do we take the loss and turn it into how do we modify the parameters? You can think about these networks as a black box with 100 million dials on the front of it. And you can set every one of those dials to a different value until the output of the black box starts giving you something with very small loss. That's the goal of the problem today. Okay, so let's say you had a function that took as input, an image, let's say an xi. And it was a function that contained 2 hidden parameters. And in this slide, those hidden parameters are p1 and p2. And let's say that for some input xi, the training data said that the output of the function should be 0. So you could actually think about this function as being the loss function evaluated on the network or something like that. We would like the function's value to be 0. But the current values of my 2 knobs, my p1 and p2 knob, the function kicks out the value 10 instead. It's wrong, right? It's off by 10. I wanted 0. The current set of my parameters gives me 10. And now what if I told you that I can give you the derivative of that function? It's a black box, but let's say you can ask it for a derivative. And you can get the derivative of that function at xi with respect to the parameter p1 and the parameter of p2. So in this case, let's say that the derivative of df dp1 is 2, and df dp2 is negative 5. So given this information, how might you design an algorithm that adjusts p1 and p2 to reduce the error, to reduce the loss? Sure.
So df, the derivative of df points into the positive direction.
Yeah, so this means that if I increase P1, the value of the function will be going up, right? And this says that if I increase P2, the value of the function will go down. So what does that suggest about what we can do, right?
If you increase P2 by 2, the error will go 0.
P2 by z, yeah. So if it's a linear function, if it was happened to be linear, and none of the examples in this lecture are going to be linear or convex optimization examples, but yeah, it says like if f of x was just linear, or sorry, in P1 and P2, well that would mean that if I just decreased the value of P2 by 2, increase it by 2, I would get the right answer, right? Presumably, like the function's value, if the slope was -5 and I walked 2 steps in that direction, I would go down 10, right? So the intuition you should have here is that, well, these derivatives tell me that I should probably decrease P1, that will send me in the right direction, and I should increase P2, because that will also send me in the right direction. And of course, like I might want to make that, and then hopefully my loss will decrease, and I can repeat this process again. Okay, what are my derivatives now where I am, and so on and so on. And the analogy that most people often make about this is walking downhill. The gradient of the function f, which is just the vector of these partials, tells you the direction that you can walk in the P1, P2 parameter space that maximally decreases the loss, or the error in the function. So in this diagram, the value of f, or the incorrectness, the loss is plotted as the color, with blue being the smallest loss. This is like the lowest elevation. And the red being the highest loss, which is the highest elevation. And if we're currently right here in this parameter space and we walk this direction, we'll be going in the right direction. Our loss will be decreasing.
Wouldn't you know it's linear if it's just scalar?
This wasn't an expression. This was like imagine I gave you a black box expression and you could evaluate it and you got this number out. Yeah, that's all. Sorry. Yeah, I mean if the derivative was constant, then yes. Yeah, that's not. That I should have said evaluated at. Yeah. Oh, I see. Okay. Yeah. Okay. So the basic algorithm that we're going to discuss today is more or less this simple. While the loss is bigger than we want it to be, evaluate the loss gradient of the network, evaluate the gradient, and take some step in that direction. And the step size is sort of it's just a parameter of the algorithm which says, well, if I'm really, really confident I can go downhill, I'll take a big step, or I might want to edge along slowly. Okay. So the question is, given this complex network with 100 million parameters, 100 million different p's, how do I compute dfdp or d-loss dp as a function of all of these parameters? That's the piece of information that you're missing to be able to execute this algorithm to train the network. Okay. Any questions so far about the setup? Because I'm trying to do a lecture on this without any assumptions that anybody has had in machine learning at all. No questions? Everybody's okay? Everybody's run Newton's method at some point, which is what you might be thinking about. Okay, so how are we going to compute dfdp for the loss of this big network? Okay. And so let's take a simpler example, and let's think about how to compute the partial derivatives of this function f of x, y, z, which is a super simple function, which you might have seen before because I took it off a very common machine learning website. But I liked their example, so I stole it from them. And I will give them credit on the slide when I post it. I just did not have time to do so. Okay, so I can rewrite this expression as a times z, where a is x plus y, because I'm going to break it down into its very basic components. I also can think about this expression as a circuit. I have an input x, y, z. Inputs x and y go into sort of the gate for the addition gate. Then I take the result of that and I multiply it by z, and so on and so on. So first of all, if I want to compute the loss, if I want to compute the derivative of the loss, I need to compute the loss. So I need to evaluate the function first. And so I can evaluate the function, and I can get out the actual answer, 35, if I did my job correctly. I hope I did. 3 times 4 is 7. 5, yes, okay. Right? So the output of the function is 35, and the value of sort of my symbol a is 7, right? Make sense? And then I can break down the derivative of this slightly more complex function of 3 variables using the chain rule. So the derivative with respect to x is the derivative of the function with respect to a times the derivative of a with respect to x. This is your standard chain rule from calculus. Okay, so, and I can also really easily compute the derivative of f with respect to a, which is, well, if f is just a times z, that's z. I can compute the derivative of a with respect to x and y. Well, that's just trivial because a is just x plus y. And then I can invoke the chain rule on these very simple derivatives that were easy to compute a much more sophisticated derivative of some composition of these simple functions. So the idea is that the whole network is going to break down into little adds and multiplies and maxes. I know how to compute the local derivatives there, and I'm going to use the chain rule to compute the derivative of these parameters over the entire network. And I can think about computing using the chain rule by moving these derivatives backwards. So I could take, what is the derivative of f? So from every node now, I want to compute the derivative of the function f with respect to the output of that node. So in this case, dfdA, in this case, dfdz, in this case, dfdx, in this case, dfdy. Well, what is dfdA? Well, dfdA is just z, right? And dfdz is just a. So I can easily compute those derivatives. And then if I want to know dfdx, how do I get that? You can just read it off. So I know it's dfdA, which is sitting right here on this wire, times nothing, essentially times 1. And so for an addition gate, I'll just take the incoming backwards derivative and push it onto its outputs. So the derivative of dfdx and dfdy will just be 5. So you can think about this process as I'm going to evaluate the network, computing the values of every output of every gate. And then I'm going to start here with the derivative of f with respect to every gate. In this case, that's 1. The derivative of f with respect to itself is 1. And then I'm going to use this and propagate it back depending on the operations all the way through the network. And I'm going to do this for all, 18 steps of the network and all 100 million parameters to compute d parameter for all input parameters of the network. So I can give you a little bit more intuition about this. So this is where we talked about, so I already showed you how addition works. So if the backward derivative, the output of the addition node has some some gradient 10, or some gradient, so that would be dfdg in this case. I decided to call the function that we're dealing with g. Well, backpropagating through an addition node just puts the value that's backpropagating on both of the inputs, because the derivative of addition is simple. It's just the derivative of each of its constituents. So how do you think? What if I changed this addition to max as an example? So we used max a lot in the last lecture, right? So we had convolution, which was addition, multiplication, and then we hit it with the nonlinear max after the convolution. So does anybody know how I would propagate the derivative through max? So let's say if the output of the max function had a gradient of 10, and it had inputs x and y, what would dfdx be and what would be dfdy? Yeah. Okay, so talk me through it.
So whichever one is bigger is the one that's actually causing that maximum.
So if I have two inputs, like 100 and 0, then the max of it will just be the identity on the larger one, essentially. So the derivative of the max is the derivative of the larger input. And the derivative, or another way to say it is the derivative of the larger input is the same as the derivative of the max. And then the derivative of the other guy is just 0. Right? So it completely just gets destroyed. Right? So if the output derivative on the max is 10, well, that just propagates to the larger of the inputs. Yes?
So here, like that 0 on the y,
Uh-huh.
the derivative of the ultimate of the
This is the overall function. So on this slide, I'm actually calling this subunit g. And g is a part of a much bigger function, let's say the whole network, f. And we're interested in computing the derivative of f with respect to the various parameter inputs of this function, right? So this is the derivative of g with respect to y, and so therefore the derivative of f with respect to y is also 0, right? So y just basically got ripped out of the equation by the max. Therefore, the change in loss as you change y is insignificant because, of course, there's an inflection at some point when y becomes bigger. Exactly. And how does it work for multiply? Yeah. So if your function is a times b, the derivative with respect to a is b, and the derivative with respect to b is a. So exactly, it's you'll take the input, df dg, and multiply it by the other side of the fence. Exactly. So if addition just passes back propagating through addition just passes the derivative through, back propagating through max routes the derivative, and back propagating through multiply just swaps the inputs and multiplies them by the derivative that's back propagating through. And a way you can think about this is well, if I change the value x by a little bit, well, that's going to be amplified by the value 12, right? Because there's about to be a multiply here. And that's the way you can think about it. Now we have all the tools to, for example, evaluate, back propagate through a single unit that we talked about last time, where a single unit would be a bunch of multiplies and adds followed by a max, right? The dot product of the weights and its inputs plus b, then taken to a max, right? So if the dot product, if this is the derivative of f, or the derivative of loss with respect to this unit, with respect to the output of the max, then it's quite easy, right? I'm just going to route that value. I'm going to route it as y, and I'm going to say, well, y is 10 if the upper input to the max is bigger. Otherwise, it's 0. Then I have a bunch of additions. So what happens next? I just got to push that y through. And I keep pushing the y through. And I keep pushing the y through. And then I have a little bit of a swap because of the multiplies. So if I change, for example, the weight W0, I know that its effect on the final loss is going to be proportional to y x0. Yeah, y x0. It's going to be proportional to x0 because that's what it's multiplied by. And then it's sort of multiplied by anything else downstream, which is where the 10 came from. And I just made that some arbitrary constant. OK. Any questions so far? All right. So far in this, I'm only using an input variable once. Right? And remember in these conv layers, I have a set of weights. It's actually being used in a bunch of expressions. So what happens if I had like x times x or something like that? So here's a simple expression that I made. What did I make it? I made it x plus y plus x squared. And so I just kind of broke it down into its components. We said, OK, well, that's a plus b. And a is x plus y, and b is x squared. So the derivative of a with respect to x is 1. The derivative of b with respect to x is 2x. And then I can just apply the chain rule to each of the parts. And I'll get the derivative is 2x plus 1. So that's how I could do it algebraically. Or I could actually just do it with back propagation and think about what should happen is the 10 gets propagated to both of its inputs. The 10 gets propagated to both of its inputs through the plus. The 10 on the multiply will get multiplied by each side of the input, by each input, 5. And so I end up with what ends up hitting the x thing, the blue numbers hitting the x would be 10 times 5 plus 10 times 5 plus 10. Well, x is 5, so that's 2x plus 1. So reuse of variables adds, which makes sense because the derivatives just add. And that's like saying, well, if this x is used in 2 different places, if I change x, well, the loss will sort of change as a result of this route. And the loss will also change as a result of this other route. So the 2 changes to the loss should just add. That one was a little trickier. Okay. And then another way to say that is, well, you can actually rewrite all this stuff. And I hope I derived this correctly, because I did it myself last night. is, well, what happens if we're not talking about scalars, we're talking about vectors? Because I talked the last time of how you can think about all of these convolators as just a huge matrix X, which came from the input values, times a vector or a matrix of weights, which every column of the weight vector, or the weight matrix, is a different filter. Okay. So the question will be, what happens if you're propagating a matrix multiplication? And it just turns out, as you would expect, it just kind of falls right out of the old scalar rules. So for example, I can ask the question, well, what is the change? So in this circuit, we have a bunch of weights, a big matrix X, and the output is the value Y, which is the result of the convolution, if you remember last time. So this is convolving the output of this matrix X times this W is, remember, convolving values of X against the weights. And so the Y, the output of this matrix vector multiplication is just the result of convolving this input image against these weights. So the question is, well, what is the change of one of the pixels in the output convolution? So what is the change in Yj, the jth pixel in the convolved output, as I change one of the weights I? Well, that just comes from looking to see what's going on. Let's go pick a particular row out of this column. And it's just the element of this matrix. It's just xji. And then if I want to sum the changes, I'll sum that up over all j's to produce a vector of derivatives. This is how every single element of the output changes as a function of wi, of the weight I. Well, this summation is just basically a matrix vector product on xji, which is basically x transpose times the backprop derivative that came back through. So this is the blue line dl dy. So you can just take the input that comes back, the vector of derivatives, and you actually just multiply it by the transpose of the matrix, and you get out dl dw. Not a particularly fundamental thing in this course, but it's just kind of interesting to see how it generalizes out to the vector form. So yeah, so the derivative of the loss with respect to the weights, what is this? What is the type of this, or the cardinality of this? You can actually just do units checking to make sure I did okay here. What is this? So before I said dl or df dx is a scalar. This is a vector, right? Because the loss is going to change differently for every change in the weight. So this is a vector. What is this? dl dy. Well, this is also a vector. This is how the loss changes as a function of the output of the whole unit. And so therefore, this needs to be a matrix that converts this loss into per weight losses. So it's all pretty clean, actually. Yeah. Okay, so that's exactly what we're going to do. We have this huge network. It's composed of multiplies and adds for convolutions, a bunch of maxes for the nonlinear units, and there might be some max pooling. Max pooling is just a max. At the end, we actually hit it with a softmax loss. I didn't tell you how to differentiate through a sigmoid, but it's actually quite easy, which is one of the reasons why people use sigmoids for that loss. So you could actually just start with the loss on your network, and then just compute d loss, these 4 parameters, and then just keep going back. And you can compute these gradients for all 100 million parameters. So for every training example, we're going to evaluate the network. We're just going to run the whole thing through. We're going to do last class. We're going to compute a loss. And then we're going to run this backpropagation algorithm to compute gradients for all of the parameters. And then given that gradient, what am I going to do next?
Use gradient descent.
I can just use gradient descent to update all 100 million of those parameters in the direction of the inverse direction of the gradient, the negative direction of the gradient. And that gives me a new set of parameters. And we do this for every single image. And then we repeat over and over and over again until we're happy with the loss. Yes? Because the gradient is pointing, well, it depends how I'm defining it, but I want to move towards negative. I want to decrease the value of the function. But yeah, because the gradient's going to take me up. Yeah. Okay, so is this, and this is basically it. There's really not much else here. So is this cool? Everybody makes sense? Okay. So there's a couple of things to notice on how the world is a little bit different from last class, from a computational perspective. First of all, there's some memory footprint issues. So let me take you, let's go back to, let's say, this, no, not that example. Let's go to this example, like multiply. So in last class, when I was evaluating the network, if I was smart, I would evaluate a layer. I could delete its inputs, evaluate the next layer, delete its inputs, and so on and so on and so on. So the memory footprint of my computation was proportional to the maximum footprint of any layer, essentially. I need to keep one input and one output in memory at a time, and I can just stream it right through. Now notice that when you're backpropagating, you need to know the value of the functions, because you need to know, for example, which way to switch the derivative in a max. Or you need to know which way to, what to multiply the derivative against while you're backpropagating in a multiply. So now I actually have to keep all of these outputs of the network around for the entire duration of the iteration, because I'm going to have to come back through and use them all on the way back up. And I actually need to keep around all the outputs and all the derivatives of the outputs as well, because sometimes you need dx as well as just x. So, we were talking about memory footprint a little bit last time, and the world actually just got a little bit worse, right? So these were the sizes of the parameters and the outputs for a common network these days. And we were a little bit concerned about the fact that there were 400 weights, or 400 megabytes of weights. And now we need to store weight gradients, and probably some other terms that I won't talk about today, like the momentum on the gradient and some other things. So all of a sudden, this number just got multiplied by 3, at least 3. And moreover, all of these have to stay, memory resident for the entire duration of the computation. And remember that all of these numbers, which don't seem very big, are actually per image. And we might be running 100 or 256 images through the network at the same time. So you can think about multiplying these by maybe a factor of 100. Right. Oh, and you have to store the derivative of the outputs, right? So think about multiplying those numbers by about a factor of 200 or so. So the training can be very, very memory footprint intensive, which causes some problems if we start hitting the maximum amount of memory you can keep on a single node. So there's going to be two reasons why we want to parallelize this computation. One is we want to parallelize it because, well, we have to run, to train this thing, we have to run 100 million images through it for maybe hundreds of thousands of iterations. And that's going to turn into hours or days or weeks of time. So I'd like to parallelize it just to make that faster. And second of all, I may have to parallelize it because all of the weights and the intermediates needed to do backpropagation may not fit in memory, or especially for big networks that people would like to create. So this is a modern academic network. The networks that they're training at Microsoft and Google these days are probably much, much larger. Okay, so here's our workload. Our workload is, while the loss is too high, for each item xi in a batch, for all elements in the batch, push it through the network, compute loss, propagate back up to compute gradients, sum the gradients over all of the images, xi. So we're going to average the gradients to kind of smooth them out a little bit. And then given the gradient, we're going to take a step updating the parameters. So if you kind of look at this thing, well, OK, so where is the parallelism, right? So, well, at first glance, this while loop is pretty much sequential, right? I'm walking downhill. I can't take 2 steps at the same time. That doesn't make much sense. We'll get back to that in a second. This loop is parallel across images, so that's very compelling, right? Like that's very compelling, except there is a reduction. They're summing these gradients all into a single gradient. So there's going to be some synchronization that we need to have here. And then, of course, evaluate loss gradient is itself a very big computation, which we talked a little bit about last time, how you might be able to implement that very efficiently using reduction to matrix multiplication, if that's in the simplest way, or direct, fancy, high-quality direct convolution for these kinds of things. So there's parallelism within this function. There's parallelism across the images. Obviously, the gradient update is trivially parallel, because that's just for all parameters, add this thing in. So you kind of see the lay of the land here, right? So this, okay, so this is going to be the workload that you're hearing a whole lot about these days. How do we train these networks quickly? Huge expense. It's going to take forever. Very large memory footprint, which is going to begin to make us make some interesting decisions. And it's not actually embarrassingly parallel. The outermost loop is not parallel. And even the innermost loop has a reduction in it and stuff like that. So it's not the easiest thing. Okay, so let's think about this a little bit. So here is, your pseudocode. And does anybody have an idea of how they might get started? If I gave you this pseudocode, I gave you evaluate loss gradient as a black box. I said it will use a bunch of cores on the machine. Where are you going to go from here? You all have a lot of experience parallelizing things. Where are you going to go from here? Yeah.
Put like the images in a queue.
Okay.
And then each core could pull either one or more sets of images, evaluate the loss gradient for all of them, and then sequentially add it to the gradient in some kind of reduction.
Fair enough. I'm going to make this a little bit harder to just really quickly. Let's assume that we want to do this on a big cluster. So you made the assumption it was parallelizing across nodes. And in some sense, the evaluate loss gradient can utilize a full node. Like you can get all the parallelism on a node out of that. That's a little bit of an oversimplification, but for the first part of this lecture, I want you to think about it kind of like in terms of like almost like when we talked about the grid solver. Just imagine there are a whole bunch of different computers. You want to parallelize it over computers, and you don't have a shared address space. But we can talk about the multi-core thing. So actually, let's talk about the multi-core thing. So what was your suggestion? You say put every one of these iterations of the for loop on a different node, right?
Yep.
Cool. Okay, so now what?
So basically just use like a work.
Sorry, on a different core, not a different node. Yeah, on a different core.
So use a work queue so that you can just dynamically schedule work on different cores.
Sure, and you may not even have to because they all are roughly the same cost. But yeah, okay, sure. Yeah, I mean, so okay, so we can distribute them across cores. Good.
You could do something similar for nodes. I mean, you could have.
I like it. So good. So this is a perfectly reasonable parallelization strategy. Are there any pitfalls? What did you have to do that? I mean, grad plus equals means every one of your independent cores is computing gradients based on its image, and then they'll all get summed together at the end, right? So is there a pitfall with that approach?
I don't think there's a huge pitfall, right? Like the evaluate loss gradient is pretty expensive, so if you have to spend a little bit of time at the end, like doing some kind of log n reduction, this doesn't seem too bad.
So that means you have intermediates, though, for every single core in your system.
So like each core increments its own gradient.
Correct.
And at the end, they all combine them.
Good. It's a good solution. Let's say you have a 32-core system. You just duplicated this times 3. Right? So your ability to scale out to multiple cores, and each of them are accumulating their own local gradients. And remember, this is a modest network, and I said in backprop, multiply the number by about 3-ish or 4. So you need about a gigabyte of footprint per execution context. So that might be fine. It might be fine, but you can see how there's going to be some limits to that approach, right? You also have a little bit of a, well, yeah. So any other ideas or refinements? I mean, I think that's a perfectly reasonable thing. In fact, if I was going to say multi-node, you have to actually duplicate these things. And so, like we're going to go in that direction. But any other ideas on how you might want to do this on a single box? Yeah? Yeah, but that's like you could say that we're gonna parallelize essentially not over the for each loop, but we're gonna parallelize in here. You could consider doing that. And now you've got a lot of fine-grained synchronization within the network, which very well might be fine. And in fact, I actually think that's a perfectly reasonable answer these days if you do it right. Yeah. You could put each layer on a different core, and then you're going to have a lot of communication between cores, which might slow you down. Potentially, you might be arithmetically rich enough. True. Yeah. I mean, you could probably work it out. That seems hard to me, though. It actually seems hard because, yeah. You could modify the parameters as you're going. You could change the algorithm. That's pretty interesting. You could just be updating the parameters, and so now everybody's working on a different set of parameters, and hopefully these updates are roughly getting you in the right direction. And in fact, that's actually how we're going to move in that direction. A lot of the solutions are actually related to that. So you can see, yeah.
If the network is not fully connected, we can divide the parameters to several groups.
You could divide the parameters into several groups, and that would be another way to parallelize the evaluate loss function, like those. Yeah, so you could parallelize the evaluation for a single image. Exactly. The other thing you could do is potentially you could all do this accumulation of the gradients sort of all into the same gradient thing, but you may have to synchronize across all the threads. Okay, so we're here. So let me change the problem to now let's say you're going to do this on late days. So you have 16 nodes on late days, and I want you to perform this computation on late days. So maybe we'll take the suggestion and we'll say, you know what? We're going to duplicate the parameter values. We're going to just copy all these parameter values onto every node of late days. And we're going to distribute the images across late days. And every node on late days is going to perform this algorithm, and it's going to compute these partial gradients, these subgradients. And then when all the nodes are done, they're going to stop. They're going to barrier right here. We are going to sum up these gradients across the cluster, and then we will perform the update the copy of the parameter values, and we'll repeat, and so on and so on and so on. So this is a pretty reasonable first start solution. There are some issues when you think about modern distributed cluster scale computing. And some of those issues are things like, we do not have a particular, like you know from late days that actually our interconnect is quite slow. It's an Ethernet connecting the 16 nodes, and the 16 nodes have supercomputer performance, and there's this baby little Ethernet connecting them there. So the interconnect can be slow. It can also be very unpredictable in performance, which would cause the cores to get out of sync. And if you're working at Google and Facebook, one of the things that's sort of the bane of your existence is that nodes just happen to have different performance characteristics, even if they happen to be the same nodes. Like there's variability in the network, there's other things going on. The machines just run at different speeds, right? So there's a lot of reasons why this whole keeping everything completely in lockstep is not necessary. And so all of the solutions that are out there, or many of the ones that have been published at least, exploit sort of the tolerance, the fuzziness of a hill climbing algorithm to say, you know what, you don't have to walk perfectly downhill. As long as you just sort of wander around and keep going roughly in the right spot, you're going to get to where you're going to go eventually, where you want to go eventually. So that's the rough intuition is, maybe we don't have to make the best decision every step, but let's make decisions that are easy to parallelize instead. Okay. So there's kind of a standard design. If you read the papers from Google, if you read the papers from Microsoft, or even here at CMU, there's a standard design which is often referred to as a parameter server. One of the systems is called the parameter server, but all of them follow this parameter server-like architecture. And the parameter server-like architecture, now we're going to move back almost to this web scaling lecture a little bit, is I have a bunch of worker nodes that are going to perform the heavy lifting of the gradient computations. And I have one node that I'm going to designate as the parameter server, and the parameter server is responsible for keeping an up-to-date copy of all the model's parameters. So actually everything I'm going to describe here is relevant to any form of distributed optimization, not necessarily neural network optimization. So this would be fine if you were trying to do logistic regression or other types of model learning as well. So, okay, so the parameter server is going to say, okay, I need to do an iteration of stochastic gradient descent. I need to do a mini batch. And so I'm going to partition the images, the inputs, the training data, onto the various nodes. So I'm going to tell them, you're responsible for these images, you're responsible for these images, and so on and so on. And they'll go get the appropriate images, right? So they'll go load that training data. And they might get it from the parameter server, but most of the time in these things, they're going to load this off of network disk, off of the database from somewhere, right? Just like in a Hadoop setting or something like that. Okay, and then the parameter server also needs to tell all these workers, hey, these are the parameters. This is the current state of the model that you're trying to learn. And I'm going to indicate the current state by saying it's parameters version 0 at iteration 0. And so all of these nodes are going to kind of do their thing. They're going to start iterating over all the images, updating their local copy of these gradients, right? So and they're called, I'm writing subgradients here to make it clear that this is only a partial gradient. It is not the gradient that's computed over all the images. It's computed over a subset of the images. And so they just do their job. And at some point, one of these nodes is going to get done with processing the images that it's responsible for. It's going to have computed a gradient from a number of input training images. Now, that might finish way before the other nodes. So instead of holding everybody up, what the node is going to do is it's going to immediately communicate that subgradient back to the master node, to the parameter server. And the server, what do you think the server is going to do with the gradient information? It could wait to receive all of them, but then we're basically back to like a barrier, right? So, sorry? It can broadcast, but what's it going to broadcast? It's going to, really what it's going to do is it's going to first of all update the parameter values. And I'm indicating that by saying, it's version 1 now of the parameter values. And of course the frequency, it might wait for multiple updates. It could do that. It could choose how frequently it wants to update and so on and so on. And then before that worker node 1 gets going again, it's going to go ahead and ask for, hey, can I have the most up-to-date copy of the parameter values for my next iteration? And so the parameter server sends it a very up-to-date copy of those parameter values. And so now it's interesting, right? Because worker node 1 is working on this set of parameters, while the other worker nodes are working on a different set of parameters. Things have kind of gotten out of sync. And it's not the same computation anymore. We are definitely going to make different steps down the hill. And then at some point in the future, right, so worker node 3 might finish its job. It says, here's my gradients. Parameter server can update its parameters. And go ahead and send the updated values back to server 3. Now, I don't have it on this diagram, but you could imagine an implementation where periodically in the middle of performing a step, perhaps any of the nodes asked for the most up-to-date version of the parameters, and the parameter server hopefully would comply, right? So the main idea of this is to move this gradient descent operation, which used to be a for loop of, for all images, compute the gradient, take the new average, the summed gradient, update the parameters, and go again, over and over and over. Now you can think about it as like all the workers are always sort of asynchronously doing their best given the current state of the system that they know about, computing some gradient based on the part of the training set that they know about, and continually pushing that gradient back to a master node. And the master node is accumulating all those gradients and making sure people have the most up-to-date value of these parameters as the computation proceeds. Yes?
So here we are assuming that all parameters can be created in one node.
Yeah, actually I have, and I didn't tell you that. But I'm assuming that all parameters can fit on a worker node because I can actually evaluate the model and its gradients on a worker node. I'm also assuming they can fit on the parameter server as well, and we're going to drop that assumption shortly. Right? Things will get a little tricky. Okay, so that's my architecture. You're all parallel systems folks. Do you see any problems with its design? Sorry? Too much communication. What do you mean by that?
Every time you need to communicate between a worker node and a parameter server.
Every time if I want the updated parameters, I do. So what's the trade-off here, actually? It's an interesting trade-off. On one hand, I could choose never to communicate with the parameter server, and I'll just train based on my subset of the data, which is a small fraction of the training set. And I won't get a very good result, presumably. On the other hand, maybe every single time I process an image, I compute a tiny little gradient, shove it off to the parameter server, and back. And that would be very heavy with the communication, but it would be basically like the sequential version of the algorithm from a numerical standpoint. Yeah?
Can you communicate
Save on communications, but it might be bad for.
So you're saying that I could communicate, I could screw the host parameter server, and I could just broadcast the gradients to everybody else, and they could update their parameters. That would be an alternative implementation, yeah. I don't disagree with that. What motivated that suggestion, I guess?
Because we're talking about like having to communicate all these parameters, and obviously like communicating to the server is not so bad. Getting all the stuff back is.
Well, I mean, you're going to have to communicate them because those gradients need to get to all the other nodes somehow. I think the problem that you're probably latching onto is they're all going through one node. Is that the problem that's bothering you? Because if I have gradients computed here, those gradients need to be reflected in parameter updates throughout the machine. Now, there's actually an optimization I'm not talking about, is you actually, and I left it out of my slides, you can actually not send the gradients. You can send the incoming backprop gradients, and you can do the matrix multiplication on the server, and so you can actually send a vector instead of a matrix. So there's some things you can do a little smarter math-wise, but that's sort of out of the scope of the lecture. Yeah?
So I mean, if you have to communicate the changes to all the servers, to all the workers anyway, is it possible to do this?
Yeah, I mean, you could say that, hey, you know, like the point being asynchronous update does not need to be single node, right? It could easily be some broadcast mechanism. But then one of the nice things about the parameter server is it's kind of like the workers ask for the updated value of the parameters when they kind of want them or know them. And a broadcast may not have that. But the perfectly reasonable implementation decisions. I can imagine somebody implementing a parameter server or a distributed parameter server that works that way, yeah?
Yeah, or could you broadcast like which node has the most up-to-date version?
Uh-huh.
And then another node, when they want the updated, just knows to which node.
Well, the parameter server always does, in some sense.
I was just saying
Yeah.
in a case that you don't have a parameter server.
Sure, yeah. So what you guys are saying, what everybody's basically saying, is that, hey, we've identified that the parameter server, a single master node, could become a bottleneck. We'd like to alleviate that. So I think that's a reasonable identification of the problem. And of course, you guys are good students, so now there's like 15 different ways you could potentially do that. And of course, what would be the simplest way to do that? Sorry? Yeah, you can make 2 parameter servers, right? Because all the workers are off there doing these really heavyweight computations. The only thing the parameter server is doing in my formulation here is just adding gradients into the parameters. So presumably it can keep up. Probably what it couldn't keep up on is the network traffic that it was required to sustain, actually. So yeah, I could very easily go to 2 parameter servers. And now how am I going to do that? Like, what's the implementation here? Am I going to duplicate all the parameters across both of the servers? Exactly. I could actually shard. I could actually take the parameter space and distribute it equally using whatever hash you care about. Hash may mean number of parameters divided by 2 in this case, would be a reasonable hash function probably. And now I can have multiple parameter servers that are responsible for receiving, updating, and broadcasting a different set of the parameters. Now that doesn't mean that like if I'm done with the subgradient, I need to send all of my parameters to both sides, right? Like half my parameters go to server 1, the other half of my parameters go to server 2 if the hash function was done properly. And I've at least reduced the load on the parameter server by a factor of 2. All the same data still moves throughout the cluster. This is a contention alleviation problem, not a communication reduction problem. That's true. If one of the servers goes down, I lose everything. That was also true before. So that hasn't changed. Now, of course, we won't talk about it very much today or in this class, but you could obviously decide to replicate the parameters as well. And all of these systems do, because they're training for 3 weeks, and things will go down. Yeah. Well, you could always do that. Like, for example, let's say one node is really, really slow. And the way I've designed this is that I've partitioned the training data statically across that. So I'd probably need to be really careful, right? Because now I have bias. And then I'm probably going to get through fewer iterations on a subset of the data, which means now what I've learned is bias towards the data that happen to be on the fast nodes, which could be really troublesome. in that the output of your network learning now depends on how jobs were scheduled onto servers, which would probably be very hard to debug, right? So I imagine to do this properly, you need to probably have some overlap. You might need to reshuffle the data from time to time to ensure that every piece of data got touched roughly the same amount of time and had the same influence. So at this point, we're sitting here with our 2 parameter servers. And now I'm going to go to the question that you asked, was what happens when I can't fit all the parameters on one node? And I mean that, like here, I've already solved that problem for the parameter server, but I still am assuming with all the workers that all of the parameters fit on one node. So far, our parallelization strategy has been input training data parallel. We're parallelizing across the training data. We're not parallelizing across the model itself, the network itself. So if this is, an example of my professor detection or my professor classification network, how would you parallelize this across nodes if these, let's say, 100 million parameters don't fit in memory and all the associated subgradients and all that kind of stuff? Mm-hmm. I don't need all the parameters at the same time. That's absolutely correct.
You load like 1/3 of it.
So I could load.
And then while using them,
So I could sort of stream them off disk or something like that, and that doesn't parallelize it across nodes, but it streams it off disk. Now remember all the intermediates. This is training. So all those intermediate gradients, the outputs here, can't just be discarded. I've got to keep them all around. So I would have to be putting outputs on disk or something like that. So I'd like to use 2 nodes so that I can fit the model in memory. So let's say that we wanted to use 2 completely different computers, 2 nodes on late days to process this network. Yeah?
Half the pipeline on one node and half on another?
There's a lot of different options. So I could make the cut here. I could say that, where does that save me? Do you remember where all the parameters were? 400 megabytes is, 400 megabytes is here, and like 100 megabytes is here. So the cut that you'd probably have to make would be this cut here, actually. And the problem with that cut is that there's a huge amount of data in the output chunks here, which was also gigabytes of data. So that's a perfectly reasonable idea. The reason why it's not used as much in practice is that if you make a cut in the horizontal direction, you either are putting a huge number of parameters on one side of the fence, or you're putting a huge number of network outputs on one side of the fence. And so it's not as useful as the cut. Okay, so if that's not the answer, which direction am I going to make my cut? Exactly. So most of the cuts slice this direction. Why is that a reasonable idea?
You can think of the network as a directed acyclic graph.
Okay.
And then, like, you kind of want to, I would think about, like, so like DFS, and you want the, think about, like, DFSing from subsets of the parameters, and you want to partition the graph so that it's roughly half of each side, right?
Mm-hmm. So if I cut here, I'm definitely partitioning both the outputs and the parameters in half. Definitely. What are the gotchas with this approach, however? Yes, sir. Oh, what are the other benefits of this approach? Yeah.
No, I was saying like most of the starting layers are convolution.
Yes.
So that means to say that like the top half of the input doesn't matter with the other half of it on the some of the output layers.
Right. So making the cut this way, if this is an image processing network, which in the running example in this lecture it is, I'm basically cutting the images in half spatially. I'm going to get a lot of crosstalk here at the end, but there's data from this pixel will not impact outputs down here because this is not sort of in the support region of an output down here, right? Because there's no way you can do an 11 by 11 convolution, a 5 by 5, and a 3 by 3 and move data more than like 30 pixels. Just won't work, right? So this is very much like this is your standard spatial decomposition like the grid solver. Is I have an image, I have all of these output volumes, and I'm just going to make a spatial partition right down the middle. Yep.
Wouldn't you have to communicate between the pixels like around the middle?
I do. So what is the communication that needs to, what pixels, what data? So I'm going to make my cut, nope. Oh yeah, so I'll make my cut this way. What data needs to be communicated between processor 0 and processor 1 now, or node 0 and node 1?
Like potentially with pixels on either side of that slice.
Yeah, it's like the ghost region, right? It's very much like the grid solver, where if I have a stencil of size 3, that means it's very, very, not much data. And where in the network do I actually have a problem, where I have a lot of communication? In the dense layers, right? So you're going to have like just a little bit of communication across the boundary. You're going to do it frequently. You're going to do it after every layer. And then down here, basically the entire 2K vector needs to move to this core. And this entire 2K of this vector needs to move to this core. So thankfully, most of the compute in the network is here. Most of the flops. And so you have a really high arithmetic intensity, math to compute ratio up here. And really, this isn't that bad, because you compute 2,000 numbers and then do a big 4,000 by 4,000 matrix multiply. So you're kind of OK. Yeah?
Could you, I mean, if that network traffic in the middle gets to be too heavy, could you just duplicate the convolution?
Oh, you could, but that's a lot of computation. Oh, you mean that? You can't quite duplicate the convolution, the computation, because it's dependent on the output. So data is moving into this region. So the amount that you'd have to duplicate is extremely large, or not extremely large, but is non-trivially large. Like imagine doing convolution after convolution after convolution after convolution. That means that like after like 3 or 4 convolutions, pixels pretty far from the boundary are impacting the output of the other side of the fence. So every step of the way, you only communicate a little bit, but it's a good idea, and that's a very halide thing to do. But these things are just a little bit, there's too much depth to apply that generally. So actually, so everything you guys are saying is right, and it's why you see, if you go read the latest from computer vision conferences or NIPS, you see people redesigning networks with parallelism in mind. So you'll actually see a trend towards much smaller spatial convolutions. In fact, people are using 1-by-1 convolutions, which for the longest time I was like completely unclear what even that meant. And you have to remember that the convolutions are also summing over all of the filter banks. They're not just convolving in space. So this community refers to a 1-by-1 convolution in a network as a convolution that's 1-by-1 in space instead of 5-by-5, and then aggregating or summing over all the outputs of all the different filters. So it's combining filters that are just grabbing a pixel from the output, from the input. And the other thing is that some of these newer networks, they're actually going deeper at the expense of much smaller, fully connected layers. So with these requirements in mind, especially if this is a cut between 2, imagine if we had to distribute this thing onto 16 processors, that boundary region is going to start getting big. And it makes sense to shrink it as much as possible. And so people are trying to combat that with new network topologies that are a little bit more parallelism friendly. So if we do something like this to partition the parameters while doing gradient descent across these 2 nodes, then we have a setup that looks like this. So we've sharded our parameter server. We've distributed the parameters across the 2 parameter servers. And in my simple example, groups of 2 nodes are working together to compute a single subgradient by partitioning the network across those 2 nodes and doing very, very fine-grained communication as shown on this slide after every step going down and then also every step coming back up with the back propagation. And you can imagine that if you wanted to do this effectively, you probably should co-locate these machines, right? They should be very close to each other with a very high performance interconnect. So this model parallelism, trying to fit a model or distribute a model onto a lot of machines, is what's saying, this really, really widely distributed cluster maybe not be the best architecture for this kind of stuff. We need a really high performance interconnect, much more like something you might have, on Titan, or what NVIDIA is trying to produce these days by putting 8 GPUs together and wiring them up with a high-speed interconnect to go in between those GPUs. The reason why you need that high-speed interconnect is so that the model can be distributed across all of those processors Each one of these has 16 gigabytes of RAM, so that the distributed training, model parallel training, will be less communication bound, right? If this was traditional GPUs, you might be reading those weights off the GPU, sending them over the PCIe bus, sending them over the interconnect. And so the benefits of model parallel training on GPUs have just simply not been very useful unless those GPUs were right next to each other. If you look at some of the recent papers, some folks used Titan to do the training. And what they observed was, hey, all this fancy asynchronous stuff is all there because the network is slow and predictability is low. If you're running on a much tighter interconnect fabric where messages get sent with roughly equal probability, in a supercomputer all the nodes do kind of run at the same speed, otherwise you send it back to Cray, then all of a sudden you can kind of just go back to these more basic synchronous techniques. And in fact, they run much better because they converge faster sometimes because you're not wandering around, you're walking straight downhill. Okay, so the final example I want to give, I want to go back to your comment earlier, was, well, how would you parallelize this loop for each item on a single machine? Different cores on a single machine. And it was suggested, which was a very good suggestion, that we could just duplicate the gradients, update the gradients on every core individually, and we'll pool them all together at the end, which was exactly what we did on the parameter server. So now that we've had this lecture, does anybody, now at the end of it, does anybody have any ideas on maybe how we could avoid this huge footprint problem? Because one answer is I could just have a single set of gradients, and before I call my atomic add or take a lock and have synchronization, which slows everything down, that's what I'd have to do, actually. I'd have to take a lock. I'd have to synchronize if I wanted to get the proper sum of all these gradients. Any ideas on how we can do maybe a little better? Yeah.
You can have a single set of gradients that each core atomically updates.
Well, that's what I was suggesting would be the norm, would be the baseline approach. Single set of gradients, single set of intermediates. Every core will atomically, or with whatever synchronization is necessary, update the gradients, and you'll have a single answer, which is the right answer at the end of the day. Agreed? Yeah.
Partition the training data evenly among all the cores.
And I have done that, yes.
Yeah, so the thing is that you compute for all your mini badges on that single core before at the end, then you add everything up.
Yeah, but that's maintaining separate gradients. That's maintaining separate intermediates, which is what I'm trying to avoid a little bit for some footprint issues. But yes, that's the other baseline method. So I would like to not duplicate my data, and I'd like to not synchronize.
Just don't care about logs.
and so you're saying that you're going to do exactly what I just suggested. I'm not going to duplicate my data, and I'm not going to synchronize. Because I'm just doing a sum reduction, and every once in a while, the coherent, maybe I'm going to have a race condition, and I might miss one of those sums, which is not all that different than having an asynchronous update of stale parameters and things like that. So that's exactly what some of these techniques that are running fast are doing. They're saying, look, we need to provide this reduction, and just screw everything you've learned in class. Just do the read modify write, and if you happen to lose an update because a couple of the parameters were there was a race condition, so what? It's a little meander downhill that you didn't need to take. And in fact, sometimes they show that it works better because it adds randomness that sort of regularizes the thing. Yes.
So couldn't the first core go from top to bottom and the second core go from bottom?
Yeah, you could probably be very careful with your scheduling strategies like we had on the assignment, which says, let's minimize the probabilities, but that actually almost kind of guarantees that they'll hit the same one somewhere in the middle. So that's actually, what you don't want to do in these things is introduce bias in what is being learned because of your scheduling strategy. So you'd be much better off saying something like, well, how about you randomize the starting time of the different cores so that hopefully they're in different parts of the network most of the time, but there's no real coherence to them, to any errors. The things that can be dangerous is when what you learn in your model is a function of how it's scheduled on the machine, because that can be really, really difficult. There's a very interesting paper from Google. It's called, I'll post it online, it's called The Technical Debt of Machine Learning. So normally, like or engineering debt or technical debt is when you hack a bunch of code and a couple of days down the line it bites you because you didn't design your software well. What they're saying is that when you design these machine learning systems, you have to be very careful about some of the decisions you make, because bias in how you implemented the system may end up appearing in your model, and that can be very, very bad and almost very, very difficult to figure out if that's actually happening. Okay, so summary here, just to close up, is this idea of you're just walking downhill. It's a probabilistic answer anyways. All I wanted at the end of the day was my 4 numbers. I wanted the number of the right category to be the highest. I didn't care if it was 62.3% or whatever. I just wanted roughly the right answer. Is that these applications have built into them tolerance for error. And that some of the techniques for parallelizing them are relying on that tolerance for error to gain efficiencies, whether it be parallelism or removing synchronization or data locality and communication. And I think that's a pretty common theme in this course, right? We originally, when I gave you the grid solver example, right, it was completely sequential. It had the dependencies like in the diagonal. And we immediately changed the problem because we knew it was an iterative algorithm. And we changed it to like a Gauss-Seidel solver, which was trivially parallelizable but didn't converge as well. And in this domain, that is something that's a very active area of research. And some people are like, gosh, we should never do this because we can't reason about these systems anymore. Other people are like, look, we don't know how to reason about the systems anyways, so who cares? This is an area of active debate. And so it'll be very interesting to see how it sorts out. There's some other interesting things that are of active debate. Like, for example, the compression work I showed you last time indicated that over 90% of the network could just be removed and you get the same performance. But right now, the only way we know how to produce those networks is train the whole darn thing and then remove stuff. We don't know how to say, well, what links did we need at the very beginning so I can train this really small thing from scratch? So perhaps there will be a breakthrough at some point where somebody says, I know something about the structure of my problem that allows me to shrink these networks by 1, 2 orders of magnitude, and that would change the game completely again on the trade-offs between a synchronous update and fitting on a node and things like that. The other thing is that people have been running these things on data centers at Google, at Facebook, or whatever. These are very much clusters of machines with low-quality interconnects. There's a lot of interest in should we be doing these types of operations on supercomputers and take that mentality towards designing the lower-level hardware infrastructure to do them. And you see, I don't have a picture here, but NVIDIA's 8 GPU tightly integrated box is one example. The Facebook open machine learning node that they released, like the board schematic design that they released, is another example of tighter integration. So it's unclear whether or not we want to pay more money for our machines, or do we want to develop algorithms that are a little bit trickier to reason about? And so the jury is out on what the answer is there.
I know we talked briefly at one point about like compressing images. That there are a number of other ways, just like decrease the size or compress images. Are those ever used in the intermediates?
Increase the size? All of the paper, like basically last lecture, absolutely was what that was. It was quantize, use 16-bit, use 8-bit, use 5-bit. They were not using, because they're not images anymore.
Right.
And by the very nature of these networks, a lot of the redundancy is being taken out as you get down the network. Like anything that survives is important to the task. Otherwise, it would not have survived. Otherwise, like the weight would have gone to 0. So the training is trying to actually eliminate things. Like if I use like an L1 regularization, it's actually trying to drive a lot of weights to 0. So presumably, a good training algorithm is eliminating useless stuff. So the compressibility is, clearly it's still very compressible, proof by last time. But it probably won't be the same types of compression techniques like JPEG or MPEG, because those are designed to be almost lossless with respect to human vision. And we want these compression schemes to be lossless with respect to the task at hand, which is a very different type of compression. Okay, so exam is next time. Go study. Tell everybody about the amazing stuff that we talked about at the beginning of class.
Do we have class on Monday?
Oh, right. So I have on the schedule that I often like to give like an untaped lecture on like parallel graphics on Monday. But that was when class used to be like early in the day. And now class is 3 to 4:30. So is anybody gonna come? So what percentage of people would come if I gave an optional, just for fun lecture on parallel graphics? Got everybody that's here. All right, I guess I'm on the hook for a lecture then. All right, okay, so we'll have lecture on Monday, if you wish. Okay.